You know all those apps you use every single day? Social media, banking, you name it. Ever stop and wonder what's actually going on under the hood? It's not magic. It's this really cool, complex architecture. In this explainer, we're going to peel back the layers on how these modern apps get built, starting with the big picture blueprint and then diving deep into its absolute heart, the database. So yeah, let's get into it. So for real, how do they work? It's all about a really well-designed system of different parts talking to each other. And to really get it, we're going to do something fun. We're going to pretend we're designing our own app from scratch and walk through all the big decisions that every developer has to make along the way. Okay, here's our game plan. We'll kick things off with a high-level blueprint, the architecture. Then we're going to zoom right in on the data engine, which is a huge choice. After that, we get our hands dirty planning the actual data structure, figuring out how to make it super efficient. And then, at the end, we'll take a peek into the future with the power of connections. All right, first up, the master plan. You know, pretty much every modern web application you use is built on this foundational pattern. It's called the three-tier architecture. Let's break down exactly what that means. This image here shows it perfectly. Think of it like a company with three different departments. You've got the presentation tier, the logic tier, and the data tier. Each one has a very specific job to do, and they only talk to each other in a really structured way. This whole idea of separating things out is what makes apps easy to scale up and maintain. It's a huge deal. So that first tier, the presentation tier, that's everything you actually see and touch. The user interface, or the UI. It's what shows up in your browser or on your phone screen. It's built with stuff like React, which is super popular for UIs, and its main job is just to look pretty, show you information, and then grab whatever you type or tap and send it off to the next layer. And in the middle, we have the logic tier. This is the engine room, the brains of the whole operation. It gets requests from the UI, thinks about them, applies all the business rules, and then talks to the data tier to either get or save information. All the heavy lifting happens right here, and it's powered by workhorse languages like Python, Java, or Node.js. And finally, we get to the data tier. I like to think of this as the application's long-term memory. Its job is to store, manage, and protect all the precious data. This is where the database lives, and honestly, making sure that data stays safe and correct is its most important job. And this tier, this is what we're going to geek out on for the rest of this explainer. So, you need a place to store all your data. But how? This brings us to one of the biggest forks in the road for any app developer, picking your database engine. The two main families are SQL and NoSQL, and they have totally different philosophies. On one side, you've got SQL databases. These are the old school, the standard for decades. They're all about strict structure, predictable rules, kind of like the perfectly organized spreadsheet. On the other side, you've got NoSQL. This is the new school, a much more flexible approach that was literally designed to handle the huge, sometimes messy datasets of modern apps. Now, what makes SQL databases so trustworthy is this thing called ACID. It's an acronym that stands for a set of guarantees. It basically means that when you save data, it's all or nothing. The data always follows the rules. One transaction won't mess up another. And once it's saved, it is saved. For something like your bank account, this is absolutely non-negotiable, right? NoSQL databases, on the other hand, often play by a different set of rules, base. They're all about being available. They say, hey, it's more important that the app is always online and fast than for every single piece of data to be perfectly consistent across the globe at the exact same millisecond. The data becomes eventually consistent. This is perfect for, say, a social media feed. So it all comes down to choosing the right tool for the right job. This table just lays it all out. SQL is that highly organized library with a strict card catalog. It's amazing for structured data. NoSQL is more like a bunch of different file boxes, super flexible, and if you need more space, you just add more boxes. That's what we mean by scaling. With SQL, you scale up by buying a bigger, more powerful server. With NoSQL, you just scale out by adding more cheap servers. Okay, enough theory. Let's get our hands dirty. Now we're going to actually plan out our data structure. This blueprint for the data is called a schema. And to make this feel real, let's design the database for a simple blog. It's a classic example, but it's perfect because it really shows off the differences in how you'd approach this. Our app needs to handle users, their blog posts, and comments on those posts. So in the SQL world, we'd build a schema with 3 separate tables, one for users, one for posts, and one for comments. See those little FK tags? That stands for foreign key. It's how we link the tables together. So to get a blog post with its author's name and all its comments, the database has to do this operation called a join, where it pieces together the data from all 3 tables. It's incredibly clean and organized. Now, check this out. The NoSQL way, especially with what's called a document database, is a totally different way of thinking. Here, we can just stuff all the information for a single blog post into one single document. The author's info is nested inside, and all the comments are right there in a neat little list. If your app is mostly just showing blog posts, this can be blazing fast because everything you need is in one place. No joins required? So no matter which path you take, you have to keep your data organized and efficient. In the database world, especially with SQL, there's a formal process for this, and it has a fancy name: normalization. Normalization is basically just tidying up your database. The main #1 goal is to get rid of redundant data. Why? Well, if you store someone's name in 10 different places and they change it, you have to remember to update it in all 10 places. That's a recipe for disaster. By storing each piece of information just once, you keep everything consistent and reliable. The process is broken down into these levels called normal forms. You don't have to memorize them, but the first 3 are the most common. The gist is, you make sure every column holds just one single value, and then you make sure that all the data in a table really truly belongs together and depends on that table's main ID and nothing else. But here's the plot twist. Sometimes you intentionally do the exact opposite. For performance, to make things faster, you break the rules of normalization on purpose. You add redundant data back in to speed up how fast you can read information. This is called denormalization, and it's a super common trick of the trade. And here is a perfect example. Remember our blog? In the before version, the normalized one, if we want to show the author's username next to their post, we have to do that join to the users table. In the after version, we just copied the username and put it directly in the post table. Now, yes, if a user changes their name, we have more work to do, but fetching all the posts to display on the main page just got way, way faster. It's all about trade-offs. Okay, to wrap things up, let's look at a really cool, special type of database that is built from the ground up to understand one thing better than anything else: relationships. I'm talking about graph databases, and they're becoming a huge deal, especially with all the AI stuff happening right now. See, in other databases, you have to figure out the relationships on the fly using those joins. But in a graph database, the relationships, the connections, are stored as actual physical things. This makes asking really complex questions about connections, like find all my friends' friends who live in my city, incredibly fast and just intuitive. The query language itself even looks like the pattern you're trying to find in your data. It's pretty amazing. So, there you have it. We've gone from the 30,000-foot view of app architecture all the way down to the nitty-gritty of how data is stored. We've seen the superstructured world of SQL, the flexible and fast world of NoSQL, and the deeply connected world of graph databases. Each one has its place. So the real question, the one I'll leave you with, is knowing what you know now about all these trade-offs, which one would you pick to power your next big idea?